for the indication. Hello everybody, welcome to the sessions of the Quantcept seminar in this new year of 2023. I welcome you on behalf of myself and the co-organizers Simone Montangero, João Seixas, Andris Ambainus and Saverio Pascazio. And today we inaugurate a new type of presentation, tutorial. So it's a great pleasure to start also this new format in our seminar. Hopefully we'll have more of these. We believe this will be helpful to continue to bring the two communities of quantum computation and high energy physics together. I pass to Simone Montangero, who will kindly introduce the speaker. Thanks, and Simone, please.
Thanks, Yasser. Good afternoon, everybody. Yes, and today I will be the chairman, and so you can simply, have your questions at the end. People are following YouTube live can write in the chat as usual. And today it's a pleasure to introduce Pietro Silvi, who is going to give our first tutorial on the role of tensor networks in simulations of Hamiltonian lattice gauge theories. So Pietro, the floor is yours.
Thank you very much. I will now share the screen.
Oh.
Do you see full large picture?
Yes.
Okay, then let me start by thanking very much the Quantcept committee for giving me the opportunity of presenting the first talk of this new year. And let's hope that the year is promising as much as the topic that I would like to talk to you about. What I would like to show you today is an incomplete overview of how tensor network methods, numerical methods for simulating quantum many-body theories, can be promising and powerful tools when addressing lattice gauge theories, so field theories with gauge symmetries on lattices. I say incomplete overview because I will focus mostly on the physical results produced by me and my colleagues in our work group, but just so that you know, this is just a small fraction of the great developmental progress that is being carried out worldwide, basically in the last decade, in applying tensor network methods, a set of numerical methods that arose in the last 20 years, to the fields of lattice gauge theories. And that will be focused on today. Lattice gauge theories, and by that, I mean all that set of, lattice theories, typically displaying two types of fields. You have matter fields and gauge fields, and their dynamics are intertwined together in order to satisfy some local constraints. If you have in mind electrodynamics, then the local constraints would be the gauge symmetry. In this case, the Gauss law, the divergence of the electric field equal to the local charge. And if we want to consider the dynamics of an electron on a lattice, then as the electron moves to satisfy the symmetry, the gauge field has to be updated. So typically we have two types of fields in this case, matter fields that live on the lattice sites and gauge fields that live on the bonds of the lattice. Very interestingly, this type of theories on a lattice in Hamiltonian formalism are a bridge, a conceptual bridge between two different spheres of physics altogether. On one side, we have very low temperature physics, such as in cold solids, cold gases. And in these senses, in these scenarios, we have particular phases, so collective phenomena where there is spontaneous arising of gauge symmetries. This is what happens in high temperature superconductors, but also frustrated spin system and so on. On the other side, we have the high energy physics and all the dynamics of particle physics. So we know that the standard model is indeed a bunch of gauge theories put together in this very peculiar, perfect design. And they do indeed have these two types of fields, matter fields that are leptons and quarks and are fermions, and gauge fields, which are bosons. Clearly, as they are intrinsically interacting theories by construction, they are demanding to be treated. So free treatment leads you nowhere. So you have a few options here. Either this theory is weakly coupled, so weakly interacting, such as Q with D, and therefore you can have an analytical treatment basically based on perturbation theory. So that means Feynman diagrams. But some theories are inherently non-perturbative, such as quantum chromodynamics. And in fact, figuring out all the collective properties of quantum chromodynamics has been a big question mark for the last 70 years or so. So it's clear that as analytical tools cannot completely solve the problems, we need numerical tools or any type of simulation tool that allow us to address these models with simulations. In the last 50 years or so, the big bulk of the work has been done by Monte Carlo methods. And Monte Carlo methods are able to compute path integrals and therefore calculate partition function in a very solid way. They have been a very solid workhorse, but they have a limitation that there are regimes where the actions are complexes and therefore Monte Carlo cannot converge in a meaningful, feasible time. These are called the regimes that give rise to sign problems, and there are a lot of these regimes. First of all, scenarios where you have chemical potential, corresponding, for example, in gauge theories in a matter versus antimatter imbalance. It's clear that we need more simulation tools to go forth in this direction. And from the point of view of technologies, specifically quantum technologies, there is the promise that quantum simulator will be the answer. By quantum simulator, I bet people already heard what this means in the sense of having a quantum platform perform the dynamics of another quantum platform. So you have a controllable quantum device, such as cold gases, trapped ions, superconducting qubits, can be a quantum computer, but not necessarily. Exhibit the dynamics of a desired unknown system. And as the technology is moving in this direction, we are still somehow far from it because still it's difficult to keep many-body system, even controllable ones, coherent for long times. So as we develop in that direction, we need an intermediate tool, a numerical tool for classical computer that can go beyond the regimes. So in those regimes when Monte Carlo cannot, but at the same time deal with the intermediate system sizes so that it will be able to be a benchmark for the future quantum technologies. And in this niche of necessity, the tensor network methods fit perfectly. They do not suffer the sign problem of the Monte Carlo, and they can allow us to access those intermediate system sizes that will be fundamental towards the benchmarking of future quantum technologies. Very good. So the necessity is there and the promise is there, but what are tensor networks? Like, as Simone introduced me that this was supposed to be a tutorial, I want to give you a little bit of an overview of what a tensor network is as a data construct and how we use it to actually do investigation on quantum many-body models on a lattice. Okay, then it will be applied to lattice gauge theories, just as we apply to non-gauge theories. So for like spin models and so on. So let me spend a little bit of minutes in reviewing what a tensor network is, what a tensor is to begin with, and how do we use them to construct a tailored many-body wave function ansatz for a many-body model. So here we go. In its simplest format, so without considering symmetries at the moment, a tensor is just a collection, a multi-index collection of complex numbers that can be considered as variational quantities, okay? So I have a matrix, for example, is a rank 2 tensor, a complex matrix, and generalization of a matrix is any rank tensor. If we have 3 indices, it's a 3-rank tensor, or oftentimes we call it tensor with 3 legs, simply because we use this graphical notation where the tensor is represented by a bullet and the indices, which are integer, are represented by incoming links attached to it, so that we can convert the mathematical construct into a graphical geometry. On top of this notation, we also have defined an operation between tensor, and that is the one that we call contraction. That is basically the multiplication of all the elements of tensors summed over all the possible values of the on the contracted index in between. It is basically matrix time vector multiplication, or matrix time matrix multiplication. And in fact, a matrix time vector multiplication we would draw in the notation of tensors as it is. So matrix time vector contracted over the intermediate link gives us what? A vector. That makes perfect sense. And there is a generalization of any type of multiplicative linear operation that we can do, can be somewhat expressed in this language. And we can even express types of contractions that are more complicated than simple matrix concatenation and multiplication. How is this useful? Because now we will gonna be using this object to efficiently represent a many-body quantum state on a lattice that normally we could not have ever hoped to represent fully, simply because it would require too much memory. What we're going to do is represent the quantum state as a collection of various tensors, each one with its own complex entries, multi-indexed complex entries, contracted over some indices. Okay, why is this the case? Why do we need to do this? And how does this help us? Well, first of all, how do we even represent the state as a tensor or as a tensor network? Well, simply imagine the state to be expanded over a product basis over the n sites of the system that you have. So you have n sites, the first site as a basis, as its own canonical basis, so does the second, so does the third, and to describe all possible canonical logical states, there is the usual construct of tensor product. Each one of these global basis states will have its own amplitude, and so the vector of amplitudes can be, in fact, written as an n-index tensor, which I can represent like this, or I can represent like this in this graphical notation I was telling you about. As you know, exact diagonalization brings you only so far, because if you don't throw away make some approximation and throw away some dummy information, you will never manage to scale the system to any reasonable size. Just to make a mental exercise, if you think that you have a number of sites in a macroscopic object equal to 10 to the 23, then the dimension of the amplitudes vector scales exponentially with the number of sites, then you would have something that has at the exponent 10 to the 23. And this is so much huger than all numbers of atoms in the observable universe. So this is nuts. It's clear that some approximation is needed to be able to manage this amount of information, compress it in a manageable way. And the way we do it is indeed, instead of representing the huge tensor, consider that the tensor of the amplitudes of a state is the result of contraction over a controllable virtual bonds of smaller tensors. You can think about doing this constructively, of course, from a conceptual point of view, but the concept is sound. You can think about doing first a singular value decomposition split, making a partition half sides and half sides left and right, ending up with intermediate bond dimension. It should be huge, but you can truncate it to a finite value, discarding the smallest values. And then you repeat until you arrive to a representation that is now manageable from the standpoint of data information, simply because the complex entries you need to manage are not anymore exponential in the system size, but they are linear in this case, or worst case scenario, polynomial. Anyway, manageable. This is a matrix product state. I'll come back to do in a moment. And it's the graphical notation. If you wanted to write it in explicit CAD notation, you would see a product of matrices as its amplitude. And that's why matrix product state. In the end, the idea is, okay, we now replace a generic super complex state with a variational ansatz that is a tensor network of the amplitude over a product basis. And for us, that is the tensor network wave function ansatz. And it's used in our numerical technology, the tensor network method. But why does this work? So in principle, you can imagine that it has to work for some value of this dimension, that is the number of kept correlations between the partitions of your system. That basically define this dimension chi that I was showing you before, sorry. It's the dimension of correlations that we keep between the partitions in the system. And as this value is completely defined by the user, is perfectly tunable. You can go all the way from 1. 1 means that your state, that your variational state, it's a product state. Or that means that this represents mean field. But then you can do mean field with some correlation, more correlation, more correlations. In principle, you could conceptually push it all the way to infinity and describe, again, a completely generic state. All right, but then how do we know that this approach will be efficient? How do we know that we will be able to describe intermediate to large sizes system with tensor network with a bond dimension chi that does not explode immediately in the system size? Well, this is due to the area laws of entanglement. In fact, it is known that physical states of finite range Hamiltonians, or Hamiltonians where the interaction decays with the range sufficiently fast enough, basically local Hamiltonians, well, they have very specific properties of entanglement. Their entanglement is low to a point that actually, if this is the whole state space, the space of states, actually all the physical states of this Hamiltonian live in a very, very, very tiny corner. And it's a very tiny corner that contains low entanglement for these bipartitions. And what are the states that live inside here? Well, there are equilibrium states of that local Hamiltonian, ground states, finite temperature states, low-lying dynamical states, and even steady states of local master equations. Okay, as long as the Hamiltonian is finite range interacting, a tensor network will represent my quantum many-body states accurately and efficiently. That is, we can take a chi that is relatively small. By relatively small, it means sometimes 100 or 1,000, and yet represent the state very accurately, even at intermediate size. And this is the reason behind this technology. Clearly, I only gave you an intuition of what is the ansatz state of the tensor network ansatz states and its concept behind it. What I'm not going to discuss are all that plethora of algorithms and methods that are based on these class of states. Mostly algorithms that are able to search for some particular states, like the ground state of an Hamiltonian, or states that implement some sort of dynamic, for example, the out of equilibrium evolution under a local Hamiltonian. And here are popular examples of the states that actually have been widely used in the literature since the 90s, basically, to carry out a very interesting calculation that led through a revolution in our understanding of one-dimensional quantum models. On one side, we have the metric product state, which are the state that for one-dimensional lattices accurately capture those area laws of entanglement that I was telling you before, and they even scale very smoothly with chi. So the algorithm, the scaling, this is the scaling cost of the algorithm for finding the ground state. This algorithm is called density metrics normalization group. You probably heard about it. And it's extremely successful because for most gapped phases, you don't need to scale the sky at all with the system size, and you can be arbitrarily accurate, which is very, very interesting. On the other side, you can imagine also doing other type of tensor network structures, something more similar to our normalization group in real space. And this gives rise to the tree tensor network, which is a personal friend of our group, since we actually use this construct a lot because it can be generalized in higher dimension. It scales a little bit worse than metric product state in 1D, but as we go to 2-dimension or higher, it keeps the same scaling. Here's the 2-dimensional situation. The natural extension of the metrics product state that I was showing you before is this projected entangled pair state. There is one tensor associated to each lattice site, in this case, a square lattice. And this tensor has one leg corresponding to the physical degree of freedom and another virtual link for each one of the lattice neighbors, okay? These states here accurately reproduce the entanglement area laws. They have the correct entanglement under bipartition. However, they have much more drawbacks than the matrix product states have. For instance, they cannot be exactly contracted. So you cannot exactly, in a polynomial time, extract expectation value from the ansatz state, though there are approximate, uncontrollable approximate strategies to actually do so. And even the optimization, even though it's polynomial, it scales very bad with this chi dimension. So there is still development being made on these steps from an algorithmic point of view. In the meanwhile, we can use the same construct that we were of tree tensor network of real space normalization that we were using in 1D, and we can be equivalently applied in 2D. In this case, you would have this starting to be a little bit ugly, but it's still quite nice if you have a picture, if you have a feeling for it as a pyramid in 3 dimensions. The drawback is, of course, that it does not reproduce correctly the area law, and this means that you have to scale that dimension chi with the system size if you want to keep the same amount of local accuracy. But since it scales relatively nice with chi, so it's only chi to the 4, we can afford to go to intermediate sizes and still be relatively accurate. We can simulate 8 by 8, 16 by 16. For some system, even 32 by 32 is completely doable. And one would argue that 900 sites, 1,000 sites, no, it's 1,000 sites. It's already quite thermodynamical limit. It's arguable, but for me, 1,000 sites is thermodynamical limit. Okay, now that I gave you a little bit of an overview of these methods and these constructs, let me take a look at the typical models that we simulate with these methods from the context of lattice gauge theories. And what we typically do is lattice gauge theories in Hamiltonian formalism, where space is discretized, but time is not. This is different from the Monte Carlo version of lattice gauge theories, where you compute path integrals after discretizing both time and space. In this case, we have real quantum variables. So time is continuous still, and space has been discretized. What wanted to say? In this sense, the tensor network framework is much more similar to what is going to be possible to do with quantum simulators, because for quantum simulator, time is going to be continuous. And the space is discretized simply out of the fact that these are going to, the qubits are localized quantum objects. So space is going to be discretized and time will be continuous. In this sense, tensor network already speaks in the language of the quantum simulator. And so this is one of the reasons why it's the perfect benchmarking tool for the quantum simulators of the future. Okay, this is one of the Hamiltonians that we simulated in the latest years in a work with Timo Felser, Mario Collura, and later on 3D with Giuseppe Magnifico. And it's the lattice Hamiltonian quantum electrodynamics. It has Fermi fields, which are in the sense the scalar field psi, corresponding to describing both electrons and positrons together. And then it has these gauge fields. So here you see the various ingredients. You have a term of staggered mass, that it's a term that is supposed to remove the fermion doubling problem. And in fact, in 1D and 2D, the fermion doubling problem is completely removed by staggered mass. This is a scalar fermion field that is meant to represent both electrons and positrons. Basically, a fermion on an odd site denotes the presence of a positron, and a fermion hole in an even site denotes the presence of an electron. This is just a matter of doing the calculation correct and approximating the Dirac equation on a lattice. And then in this term here, that looks like a hopping, it's a hopping, but it actually represents an event of electron-positron creation or annihilation. You see immediately the coupling between the Fermi fields and the gauge fields. This U is in fact one of the operators of the algebra of the gauge fields that lives on the links of the lattice, as I was saying before. And beside the coupling between matter and fields, there is, of course, the pure Hamiltonian of the gauge fields, which corresponds to the 1/4 F mu nu of the quantum electrodynamics, B squared plus E squared. And in fact, B squared plus E squared, we see here the E squared term, so the electric energy density, which looks like a local term, and the magnetic energy density that looks like a plaquette operator over a square. This is, of course, an approximation, and it's the Kogut-Sussking prescription from the late 60s. It is not necessarily the most convenient way to go to the thermodynamical limit. It's argued that including larger plaquettes could actually lead to, or to the continuum. It is argued that using larger plaquettes in the Hamiltonian could lead to faster convergence to the continuum limit, but for us is an excellent exercise because it's already quite complex that requires us to work out some gymnastics. And the first gymnastics that we do is to consider this gauge field that is an infinite dimensional local space and to basically reduce it, truncate it to a compact space, which is an exercise that we typically do with bosons. And since we work with bounded energy, so we work at finite energy bandwidths, we consider only the states below this energy bandwidth, and above we just don't consider any states. This way we can keep our spaces finite, which is required in order to run our tensor network methods. And in this sense, as you see here, we basically modify the algebra of the gauge fields into an algebra of spin. In the limit of larger and larger quantum spin, the two algebras perfectly correspond. And so we are doing something that can be brought into a limit and recover the original quantum electrodynamics theory. In the limit of large spin representation, and then thermodynamical limit, and then continuum limit by peculiarly tuning the parameters. So basically, here's what we do. The results that I'm going to show you corresponds to the simplest non-trivial representation, that is the electromagnetic field corresponding to a spin 1. So 3 levels, corresponding to no electric field or one quantum electric field going to the right in this horizontal bond, or one quantum electric field going to the left. And as there are these three states, you can imagine the typical event coupling matter and fields in this electrodynamic Hamiltonian corresponds to, let's, for example, start from the vacuum. And then you have this hopping term corresponding to a creation of an electron hole, of an electron-positron pair. And this must happen while the field in the middle gets updated. And in fact, by putting the field to the right, or in this case, spin up, we have protected the Gauss law in each dressed site. This trick of the dressed site is exactly what we use to construct conveniently the local basis for the dressed site in tensor networks. So here on top of that, here on top, we have that Gauss law written in terms of lattices. So basically the charge minus the electric fields outgoing from a site, so in the dressed site, has to be equal to a value that corresponds to the background of charge that we decide. And we can decide it to be 0. That's the typical scenario. And this allows us to select some configurations that are allowed on a dressed site, that are allowed by the gauge, from some other that are not allowed. It is convenient at this point. This is a choice that me and my work group do. It's not necessary. I know that other work groups do it differently, but this is our technique. We simply consider all possible allowed dressed site configuration as canonical local basis for one site. And then we only have to remember that on two neighboring sites, the electric field in between must be the same in both dressed sites. This impacts the Hamiltonian as a selection rule, that is diagonal in this case, as a selection rule between states at every pair of nearest neighbor. But there is a positive side to this formalism, that is, even if your gauge theory was non-abelian and you decide to do this local selection rules to define a local basis, the nearest neighbor selection rule on the state would still be abelian. And we all know how it is much easier to deal with abelian symmetries than non-abelian. This is one of the reasons why we actually perform this technique, let's say. And once we have the machinery set up, we can use the typical methods from tensor network to infer physical quantity at equilibrium or out of equilibrium. Here I will show you some results at equilibrium in the case of two-dimensional QED on a lattice, where we in principle could tune the bare mass electric coupling and magnetic coupling of the theory altogether in order to observe phase transition, like this transition from a small fluctuation with respect to the vacuum that happens at positive bare masses to a crystal of charges that occurs instead at negative bare masses. And we can see the impact of the phase transition, for example, at zero magnetic coupling as a function of the electric coupling. Basically, we observe the existence in this case of a phase of crystal of charges, positron, electron-positron pairs in a dimerized way. So every electron finds a positron partner and establishes a dipole with it, with electric field in between. This is basically a product state, but as soon as we turn on the magnetic coupling, you establish a resonance valence bond state between all these possible dimer configurations. So as the magnetic coupling gets activated, you go into this resonance valence bond state, which is very interesting. And you actually see that you have half a quantum of electric field between each side, actually a quarter of a quantum of electric field between each side. Very interesting. We were pointing out peculiarities on how tensor network can go beyond Monte Carlos. And in this sense, we can perform simulation a fixed imbalance of charge. So we select how many electrons minus positron there are and run a ground state simulation in this regime. In this case of reasonably balanced electric field and masses, we actually do see exactly what we expect from a conductor, so that the residual charges that cannot be annihilated get expelled towards the boundaries of this conductor, which is very physical. So in this sense, we are recovering from the microscopical model of quantum electrodynamics, collective behaviors that are extremely intuitive from our knowledge of, for example, classical electrodynamics. And that was 2 dimensions. More recent years, 2021, we went to 3 dimensions to test some properties of confinement, of asymptotic confinement of quantum electrodynamics that can be only observed only in 3+1 dimensions. The model is roughly the same. We still have fermions and staggered fermions that do not completely resolve the fermion doubling, but we don't care too much about that. And now the magnetic field has 3 plaquette terms, right? XY plaquettes, XZ plaquettes, YZ plaquettes. So it's becoming a little bit more complex, but our technology is sophisticated enough that we can deal with all this complexity. Still considering the smallest representation for the electromagnetic fields. And as before, we select as local basis for addressed side all possible configuration that satisfy the Gauss law up there. The dimension increased a lot from the 36 that it was before. Now it's on the 300. So it requires some muscle, but it's within the capabilities of our methods. And what we do actually evaluate and study the properties of the ground states, including, again, phase transition from charged crystals to fluctuation above the vacuum, and figure out if they are second-order critical points. That seems to be the case. Just like before, we see the transition between fluctuation over the vacuum to the dimer phase in the charged crystal, and the dimer becomes a resonant valence bond state as soon as we turn on the magnetic field. So all of the properties, even the quantum correlated ones that we found in 2D, we found the corresponding effect in 3D, but we can do more. First thing that we can do is to consider a scenario where we change the boundary condition. For example, we can put von Neumann boundary conditions on 2 opposite blades. For example, we can actually put 2 plates of a capacitor. And in fact, what we expect to see, and that is exactly what we see, is that while in the case of large bare masses, you actually see the constant electric field going from one blade to the other of the capacitor, exactly as classical electrodynamics. As the electrons and positrons become more and more lighter and lighter particles, you actually do see the spontaneous creation of electron and positron pairs whose purpose is to deplete, to screen the blades and actually destroy the electric field in between. This is a very known mechanism. It's the quantum capacitor version of the Schwinger mechanism, and we do see it at equilibrium in this case, but it can be also seen out of equilibrium. Once we turn on the magnetic field and we move ourselves to the weak coupling regime, that means magnetic coupling much larger than the electric coupling, we can explore the realistic phase and expect even to go in a regime of the quantum electrodynamics reproducing the Coulomb phase, correspondingly the asymptotic deconfined phase, which is what we actually see in the universe. We do see isolated charges, which means electric charges. That means quantum electrodynamics must be deconfined given this coupling in 3+1 dimension. And this is exactly what we see. We actually consider two charges, we pin two charges, and then we consider the energy of their interaction as we pull them apart slowly. And we observe two very different regimes at strong coupling and at weak coupling. On strong coupling, here below, we see an initial increase of the energy of the pair because the electric field string is growing with its length until it is convenient to create an electron-positron pair in between. And at that point, the increase cracks, and then you have a plateau where the energy does not increase anymore. And this plateau, the position depends sharply with the bare mass of the electrons and positrons. Conversely, in the weak coupling regime, we have a much smoother dependence on the distance, and the interaction energy, which is the energy at zero minus the energy of infinity of a pair, it's completely independent of the electron-positron masses. That means, and look, it's well the energy profile, it's well approximated by 1 over r. That 1 over the distance. So that means that in this regime of weak coupling, we kind of reproduce the known Coulomb potential between these two particles, and observe that it's not an effect related to the creation of matter and antimatter, but it's spontaneously coming from the interplay between electric and magnetic coupling. So we were quite happy about this result. And I see that I'm running out of time. So let me just gloss over other types of interesting studies that we do in this direction. We are not limited to abelian gauge theories. We can do also non-abelian gauge theories, such as Young-Mills. We like Young-Mills because the Young-Mills are the standard model type of dynamics. And here's what Giovanni is doing. We are not limited of doing, of course, equilibrium. It can may as well go out of equilibrium, and that's what we do. For example, we can simulate in real time scattering processes. We prepare two isolated particles in the quasi-particles. In this case, the quasi-particle have to be a meson because it's quantum electrodynamics in 1+1 dimension, and the theory is confined, so the quasi-particle has to be a meson, and we scatter them one against the other, and we actually see the creation of entanglement in their internal degree of freedom. And the internal degree of freedom is basically the stretch phonon, which is a very interesting result, in my opinion. It's entanglement in internal degree of freedom coming from a scattering event, which is very interesting. Also for our quantum technologies applications. What we are also interested in quantum chromodynamics, because that's the true goal. The holy grail would be to go quantum chromodynamics in 3D with the flavors. It's a long road to get there, but we are moving steps, and not baby steps. We're moving reasonable steps in that direction. We already have abelian theories in 3D, and we have quantum chromodynamics in 1D, where we already observed that with two flavors, we actually get a P-wave superconductor with symmetry-protected topological order. But I don't want to bore you with more details. What I hope that I convinced you today is that the tensor networks are an extremely promising tool, and specifically within the numerical tool, and specifically within the context of lattice gauge theories, they will play the fundamental role of bridging the Monte Carlo simulation of yesterday and the quantum technology simulations of tomorrow. In between, we have tensor network. In between, we are working right now. Thanks a lot for the attention.
Thank you very much, Pietro. Are there any questions? Curiosity.
I always have the same problem. I mean, up to where can you solve the sign problem in lattice gauge theories with this? I mean, it's always solvable, or
So if you're asking me about Monte Carlos, I'm not a Monte Carlo person.
yeah,
Okay.
I know.
Okay. For tensor network, this is not a problem at all, because what we are actually doing is a variational method. We define a variational class and we optimize, for example, if we want to do a state search, we optimize a functional. Since there is no action in this case to be considered, we don't have a sign problem at all. So
Okay.
tensor network methods are completely sign problem free.
Okay, thank you.
And by the way, that's exactly why we work with the Hamiltonian and not the Lagrangian, because we never have to calculate an action.
Yeah. Okay, I understand. Thank you.
I mean, honestly, we also have, tensor network also have their obstacles to overcome, but they are completely different than the same problem.
Any other questions, comments?
Yeah, I have a question. Hi, Pietro. Thank you for the nice talk.
You're welcome.
So you were talking about how you form states that are gauge invariant, essentially by contractions at the sites and multiple spatial dimensions. How do you characterize these states a little bit more specifically? Like, what are the quantum numbers that you use?
Okay. I was trying to give you an example. Specifically for this quantum electrodynamics case, right? So let me go back to that case where I was doing. So first of all, let me reiterate that this is not the only way to go, okay? Tensor networks have a built-in strategy to take care of symmetries. Basically, you do it like this. You see the links, these links, the virtual links. I told you before they are just indices, right? They are just integer indices that don't play much, but actually there's more to it. They're not just indices, they are representation spaces of the symmetry group on the lattice side, on the physical space. The physical symmetries are raised into the virtual indices. And this is quite peculiar. So a tensor network can embed any kind of symmetries inside the tensors because the symmetries are lifted from the physical space into this virtual correlation space. So in principle, you can always do the most generic thing that you don't do. You just consider a tensor network and make it enforce all the symmetries that you want. This is a specific technique that we use to simplify our life a little bit.
So my question is less so about how you build gauge symmetry into it, but how you are enumerating all of the states in the Hilbert space. Just because I'm familiar with ways of doing this in multiple spatial dimensions, but they can have problems with multiplicities of states or not capturing all the states. And specifically in non-abelian, it's not a problem here with the theory that you're showing.
Okay, I see. Well, then maybe you can illustrate to me a little bit more. What I can tell you is that you don't need to characterize the whole global states, but you only need to characterize the states locally, because intrinsically the tensor network has a structure that he only cares about things, the spaces, the local spaces, and then these local spaces will be conjoined at the virtual correlation space level. So what we only need to list is all the configuration that makes sense locally. Of course, as you can imagine, these symmetries are all intertwined, right? Because the symmetry involves the matter fields and the gauge fields around it, but then that gauge field also is neighbor to another matter field. So each gauge field belongs to two symmetries, so to speak. So it's a matter of how you prefer to manage to put these symmetries together. We have found this technique that we choose that is to actually consider basically double, you take your gauge field, you kind of double its degree of freedom. It's called it's a technique that is called breaking a gauge field in a lattice gauge field into rations, 1 and 2 rations. And basically, make sure that a ration to the left satisfies the Gauss law on the side to the left. The ration to the right satisfies the Gauss law on the ration to the right. And then you need a nearest neighbor selection rule so that the state on the right of this ration is compatible with the state to the left of this ration. And the trick is that even if your gauge symmetry is not abelian, this selection rule is abelian.
Right. Yeah, I'm familiar with this concept.
Okay.
Because
then I still don't understand your question. My apologies.
Well, no, I mean, I work on the loop string hadron formulation, which is very similar, and it has that same sort of conclusion that this can be formulated in terms of abelian constraints only. But
okay, it's not that we invented anything new, eh?
Right. The question, that's why I'm asking about what the quantum numbers are, because it's all about, at the end of the day, how are you characterizing these basis states? How are you enumerating the Hilbert space?
Correct. You saw before we were considering a truncated representation of the electric field. Similarly, we can do something similar for non-abelian theories. Basically, we truncate based on the quadratic Casimir of the representation for non-abelian gauge. Okay,
right.
So it's still like in the quantum electrodynamics case, it's still a truncation based on the electric coupling. Okay, and you can argue that this might be tricky when going towards weak couplings, because in weak couplings, the natural bases are not the electric bases, but the magnetic bases. And I would say, yeah, okay, we can understand this, but if we want to go quantum chromodynamics, we are interested anyway in strong couplings.
Well, yeah, I mean, ultimately, one does also want to take the weak coupling limit there too. So it's,
okay, fair enough. But anyway, so there are ways
getting the same complaint when I get talks.
It's like the only way to do it rigorous is to be sure that you're at convergence in all the approximation you make, and the continuum limit requires convergence in this large representation limit. So we have to take larger and larger representation until our results are perfectly converged. This is the most sound, but we have ideas on how to get in this direction that I cannot divulge because Simone will kill me.
Understandable. Okay. Thank you.
You're very welcome.
Okay. Are there any? We have a couple of minutes more. Any other comments or questions?
Can I make just a curiosity? Thank you very much for your talk. I would ask you concerning the capacitor in QD in 3+1 dimension. Do you think it is possible to simulate using tensor network Casimir effect in that case? I mean, including a control parameter in order to move one plate with respect to the other.
Definitely, we actually wanted to do it, and then we didn't for time constraints. But yes, we thought about it, and definitely.
So it should be used with the time-dependent variational principle, or time-evolving bulk decimation.
Oh, you would like to do it dynamical? Oh, okay. I was thinking more like quasi-diabatic. So I would rather do it quasi-diabatic, like tuning the actual distance of the two plates to actually see the energy differences. But one could do it also dynamic. I would have to think about it.
I mean, anyway, they are different Casimir effect. There is the static and dynamical one. So
I was thinking about the static one. Yes, and also I'm thinking about it a posteriori. This was like 2018, 19. I would do it differently because now here we put the charges, we pin the charges inside the system. But something smarter that we could have done is to actually select von Neumann boundary conditions for the electric field, which would be more sound. this is what we should have done back then. I realized it later. Well, sorry, it's always like that. And in that sense, I think that the equilibrium Casimir effect would be, one would say, relatively trivial, but relatively trivial after all the convergences. So it's still, before you actually get physical measurable quantities in universal system units, you have to be at convergence, you know, in the sizes, in the representation, in the continuum limit, and so on. And all the limits have to be taken care of while choosing a fixed natural distance between the two plates. So yes, Casimir effect, I'm sure it could be done in principle with tensor network. There are no conceptual obstacles. There are only numerical obstacles. So being able to do all these convergences one after another, which is demanding. Not impossible, not conceptually difficult, but demanding.
Wow, thank you very much.
Great, thank you. I think that now we can thank Pietro again.
You're very welcome.
I would ask Raffaella to set up the slides to announce the next seminar, and I will leave Yasser for doing the job.
Thank you. Okay, you could do it, but so let me also thank Pietro for the great seminar and Simone for the chairing. And so the next seminar on the 8th of February, we'll have Zoreh Davoudi from Maryland talking to us about a quantum simulation program for QCD. So next slide, please. So I just want to thank all the organizers. So Simone, who was chairing, and as well as Andres, João, and Saverio, and also the local organizing team, Rafaela Ribeiro and Matteo Turco, who make sure this electronic infrastructure is working. So thank you very much, everybody, for joining this first session of 2023 and our first tutorial in our seminar series. We'll have others and see you on the 8th of February. Thank you very much and have a good day.
Thank you.